This section introduces the core concept. We're using the Johnson-Linden-Strauss lemma to shrink the size of our data while keeping most of its important information. Think of it like making a detailed map smaller, but still keeping the key features like roads and buildings recognizable. The lemma is a mathematical tool that helps us figure out how small we can make the map without losing too much detail. It's like a really powerful tool for reducing the dimensions of data. I'm working with a dataset that has 1,000 features, which is a lot. I want to reduce that number while keeping at least 90% of the important information. The function _Johnson_Linden-Strauss_min_dim_ from scikit-learn helps me do that. It's a key function within the Random_Projection module of scikit-learn. I need to understand what this function does, and more importantly, what it doesn't do, to answer the questions that follow. This is the core of the quiz. I'm presented with some statements about the Johnson_Linden-Strauss_min_dim_ function, and I need to choose the ones that are true based on my understanding of the lemma and how scikit-learn implements it. This statement is incorrect. The function doesn't give me the perfect number of components, it gives me the minimum number needed. There might be more components than this minimum that would work even better. It's more like a starting point, rather than the final answer. This one's also wrong. While I get a lower bound, using a larger number of components than this minimum isn't always a bad idea. In the real world, our data isn't always perfect, so using a higher number of components might give me better accuracy. Sometimes you need to be a bit more generous than the minimum to get what you want. This statement is correct. The accuracy of the Johnson_Linden-Strauss_min_dim_ function relies on the data meeting certain conditions. If the data is very different from what the function expects, the results might not be very precise. That is why the accuracy depends on the data distribution. Nope, this is false. The process is probabilistic, so it only approximately preserves the variance. It doesn't guarantee exactly 90%. It is a probabilistic method, and there is no certainty that we will be at 90%. It's about getting close, not hitting the target perfectly. We're tackling a dimensionality reduction problem. I want to shrink a dataset with 1,000 features, but I need to keep at least 90% of the original information. I'll use scikit-learn's _random_projection tool to do this. This statement is incorrect. The Johnson_Linden-Strauss_min_dim_ function doesn't give you the single best number of components to hit exactly 90% variance. Instead, it provides a lower bound. This is also wrong. While Johnson_Linden-Strauss_min_dim_ gives a minimum number of components, using a slightly higher number isn't necessarily wasteful. In real-world data, it might help to preserve more variance and improve accuracy. This statement is correct. The accuracy of the function depends on how the data is distributed. The underlying math makes assumptions about data distribution, which may or may not hold in real-world datasets. If my assumptions are not valid, the results may be off. This is false. The method is probabilistic, meaning that it doesn't make guarantees. I can't expect it to preserve exactly 90% of the variance. It's an approximation. This question asks you to evaluate statements about the Johnson_Linden-Strauss_min_dim_ function, which helps estimate the minimum number of dimensions needed for dimensionality reduction while approximately preserving distances between data points. I'm testing your understanding of its capabilities and limitations. This statement is false. The function doesn't calculate the exact optimal number of components. Instead, it provides a lower bound, meaning it gives you a minimum number of dimensions you'll need, but you might need more to achieve precisely 90% variance preservation. This statement is also false. While it provides a lower bound, using a substantially larger number than this lower bound isn't inherently wasteful. In practice, using a higher value can actually improve variance preservation because the theoretical lower bound might be too optimistic given real-world data. This statement is true. The function's accuracy relies on assumptions about how your data is distributed. If your data doesn't fit these assumptions, the lower bound estimate may not be very accurate. Think of it like this. If you're trying to pack oddly shaped boxes into a truck, a formula for perfectly square boxes won't work as well. This statement is false. This function gives an approximate result, it doesn't guarantee that precisely 90% of the variance will be preserved. It's a probabilistic method, not a deterministic one. We're using random projection, a technique that shrinks the number of features, dimensions, in our data while trying to keep the important information. Think of it like summarizing a long story. You want to keep the main plot points without losing too much detail. Our specific challenge. I have a dataset with 1,000 features, and I want to reduce the number of features while making sure I don't lose more than 10% of the information, variance. It's like keeping at least 90% of what's important. I'll use the _random_projection module from the scikit-learn library, which is a powerful tool in Python for this task. It's a convenient way to perform dimensionality reduction. Within that module, I'll use the Johnson_Lindenstrauss_min_dim function, which helps me estimate how many dimensions I need to keep in order to approximately maintain the distances between data points. It is based on the Johnson-Lindenstrauss lemma, a mathematical result in dimensionality reduction. The Johnson_Lindenstrauss_min_dim function doesn't give me the single perfect number of dimensions. Instead, it provides a lower bound, a minimum number, of features to aim for. It's like saying, you need at least this many features to have a good chance of keeping your data's important structure. Using more than the minimum could potentially improve results further, while using fewer is too risky and might compromise data integrity. The accuracy of this lower bound is tied to how the data is distributed. The function's underlying mathematics assumes a certain type of distribution, similar to a uniform spread. If my data doesn't match this assumption, the estimate might not be as accurate or precise. It is crucial to remember the Johnson-Lindenstrauss lemma's assumptions and limitations. I see that you're asking about whether the Johnson-Lindenstrauss function directly finds the perfect number of components to keep 90% of the data's variance. The answer is no. This function actually gives us a lower bound, a minimum number. It doesn't guarantee the absolute best number. It's like saying, to reach the top of the mountain, you need at least this many steps, not telling you exactly how many steps you will take to the summit. It's a starting point, not the ultimate solution. Let's talk about whether using more components than the minimum suggested by Johnson-Lindenstrauss is a waste. I'd say it's not always wasteful. While the function provides a lower bound, going above it can sometimes be helpful. Think of it this way, the lower bound is a safety net. Going slightly above it can give you some extra insurance, resulting in better variance preservation, especially if your data doesn't perfectly follow the assumptions of the Johnson-Lindenstrauss lemma. It depends on the situation. This statement hits the nail on the head. The accuracy of the estimate from Johnson-Lindenstrauss depends heavily on how your data is distributed. The method relies on certain assumptions about your data, and if those assumptions are wrong, the estimate might not be as good. It's like trying to measure the height of something with a ruler when the surface isn't flat. It won't give you an accurate measurement. This is incorrect. The Johnson-Lindenstrauss function doesn't offer a guarantee of exactly preserving 90% of the variance. It gives an approximation based on probability. Think of it as a good estimate, not a precise measurement. The method is probabilistic, meaning there's always a chance of some error. It's like saying, I'll probably get there around 90% of the way, not, I'll definitely get exactly 90% of the way. I'm using the Johnson-Lindenstrauss lemma, a mathematical tool, to shrink the size of my data while keeping its important features. It helps me reduce the number of variables, dimensions, in my dataset without losing too much information. Think of it like summarizing a long book into a short, exciting trailer. You lose some detail, but you still get the main idea. I have a dataset with 1,000 different characteristics or features for each data point. For example, if I'm analyzing houses, each house might have 1,000 different features like area, number of bedrooms, location, etc. I want to make this dataset smaller and easier to work with. This is a function from the scikit-learn library. It helps me figure out the minimum number of dimensions I need to reduce my data to. The n_samples is the total number of data points in my dataset. and EPS represents the acceptable error or how much information I'm willing to lose. It's like saying, I want to reduce my data, but I want to keep at least 90% of the important stuff. The function Johnson Lindenstrauss min dim gives me a lower bound, meaning the smallest possible number, k, of dimensions I need after reduction. It's not the perfect number, but a starting point. I could use more dimensions than what the function suggests, and sometimes it is a good idea for more accurate results. This question tests my understanding of how the Johnson Lindenstrauss min dim function works. I need to analyze different statements and decide which ones are true or false based on what I know about the function and the underlying mathematical principle. I'm asking you to assess your understanding of the Johnsonlindenstraussmindim function. This function helps us estimate the minimum number of dimensions needed when reducing the dimensions of our data while trying to preserve the important relationships between data points. We'll look at several statements and see which ones accurately describe what this function does and doesn't do. This function is the heart of the matter. It's part of scikit-learn's Randomprojection module, which is a tool for reducing data dimensionality. The function's input includes the number of data points and a parameter, epsilon, that controls the acceptable error in preserving the distances between data points. Its output is a lower bound, not an exact number, for the number of dimensions you need. To use the Johnsonlindenstraussmindim function, you provide it with two things. First, the number of data points you have, and second, a value called epsilon, which represents the level of acceptable error. A smaller epsilon means you want to preserve distances more accurately, but it will require more dimensions. It's a trade-off between accuracy and dimensionality. The function returns a value. That's the minimum number of dimensions needed to preserve distances between data points, within the acceptable error, epsilon, you set. It's crucial to understand that this is just a lower bound. You can, and often should, use more dimensions to achieve better accuracy in practice. I'm working with a dataset here that has 1,000 features, which is pretty high dimensional. It means each data point has 1,000 characteristics. This is where dimensionality reduction becomes really important for efficiency and performance. I'm employing a technique called Randomprojection to decrease the number of features while attempting to preserve the underlying structure of the data. This method is efficient and uses the Randomprojection techniques powered by Johnsonlindenstraussmindim for dimensionality reduction. This statement is incorrect. The Johnsonlindenstraussmindim function doesn't find the single, best, number of dimensions. Instead, it gives you a minimum. There might be better numbers of components, and the optimal number might depend on factors beyond the scope of the lemma. This is also false. While the function provides a lower bound, choosing a substantially larger number of components isn't necessarily wasteful. In real-world data, going beyond that lower bound can actually help preserve more of the variance and relationships in your data. This statement is correct. The accuracy of the function's output depends on how the data is distributed. The underlying theory relies on some assumptions about the data, and if these assumptions aren't met, the results might not be as reliable. This is incorrect. The method is probabilistic, meaning there's no absolute guarantee of preserving exactly 90% of the variance. It provides an approximation, and the actual variance preserved may vary.